That's over 5 years, but we have the full intent of doubling, if not more, those resources in order to push this forward. Now, in terms of this audience, the progress that's going to be made in these systems is probably going to rely more on the engineers, the physicists, the chemists, than it is on the biologists. And simply because we're moving into an era where we're increasingly engineering these nanomedicines to exhibit the kind of therapeutic properties that we want. And so that's so for those of you that don't know anything about the field, I'd say it's really quite a good time to get in, simply because a lot of the initial work has been done. The principle is there, but the range of opportunities now resulting from that is really enormous, as I'll try and point out. Okay, so what we're dealing with is nanomedicines, and I always characterize these as being the next generation of pharmaceuticals. And so, what do I mean by that? If I can get this thing to change, I can tell you. This is blocking this.
So it was advancing on the screen.
What was advancing on the screen? Just not here. Okay, right. Interesting. Yes, there we are. It's just taking exactly the same on my screen. So first generation of pharmaceuticals are small molecules. For those of you that take an aspirin or you have some relative who's been treated for cancer, they're usually using small molecule drugs like ibuprofen, whatever. The reason they're small molecules is because they're the only things that can get inside cells on their own to affect something inside a cell. So that really constricts you to a range of molecular weight around about 500, between 500 and maybe 800. And so the second generation pharmaceuticals are the biologics, monoclonal antibodies, and you've heard of those in various contexts. The third generation are going to be smart medicines, nanomedicines that, first of all, really improve the therapeutic properties of the small molecule drugs. In many cases, no wonder they work at all. And then enable genetic drugs, or drugs where you're using big molecules based on RNA or DNA to affect processes inside the cell. And there's this one here that's particularly exciting. Also, of course, there's the diagnostics for detecting and diagnosing disease. So examples of nanomedicines, this is just for orientation. You might have a 100 nanometer system or 80 nanometer. We usually work in the 80 nanometer kind of range, so we can go from 20 to 100 quite easily. These are systems that have a drug on the inside. You can make these systems so they're stable, so they circulate a long time. They will, in some cases, go to a site of disease, but not very efficiently. These systems here are the same made of lipids also, but they have a solid core. We've now got ways of encapsulating DNA, RNA inside these systems in an efficient manner. And then a diagnostic application would be where you may have an imaging agent on the inside and detect that from the outside. Using MRI or CT or whatever other technique one is using. So UBC and Canada, we're world leaders in the area of nanomedicines. So 6 of the 10 nanomedicines that are approved by the FDA and the US FDA and the European Medical Authority were developed here in Vancouver. So one of the reasons we got this NCE is simply because we have, as I say, right now a globally leading track record in this area. So what we have to do now is maintain that. Most of these are cancer drugs. So it's cancer drugs inside of the nanoparticle, and then they reduce the toxicity of the drug, and in some cases enhance the activity. We also have a nanomedicines commercialization hub here, primarily here in Vancouver, and this is just some of the number of spin-off companies, more than 20, about 15 of them are local. We have various manufacturing devices for making nanoparticles that are sold by some of these companies. There's CROs that have done a lot of work with international pharma and biotech. We created over 500 jobs, and as I said, as a result of these efforts, we've managed to get quite a few drugs approved worldwide. So we're building on that we're building on that to taking advantage of really an exceptional academic infrastructure. 17 universities across Canada are associated with the Nanomedicines Network. These are just summarized here. I'm not going to go through them all. So you use 60 PIs, so it's a large infrastructure. We will only be actually doing at any one time about 25 projects, so there's a bit of a competitive edge here in terms of getting the funding out. But we aim to, as I said, use the funding we have to synergize or to gain much larger funding efforts. So what we're doing is we're improving small molecule drugs. Essentially, what we want to detoxify cancer drugs and make them much more effective. Enable gene therapy. This is essentially to treat any disease you care to name. It's quite remarkable how freeing the gene therapy is. And then the area of diagnostics, which is actually a bit behind the other two applications to develop systems that give improved earlier detection and more accurate detection. Okay, so the objective of the network is to really develop 10 new drugs, and five new diagnostics, 10 new companies. We'll certainly be creating 100 new jobs. I think we'll certainly do 300 or 400 by the time we're finished. And there's a big training component in this area. The companies in this area are growing rapidly, and the opportunities for employment are quite notable. Anyway, so why are these things really of interest now? I should say this is a relatively small group, so if you have a question, stick up your hand and we'll do this informally. The technology is increasingly clear to enable improved delivery of small molecule drugs to disease sites, in particular cancer applications. As you're aware, there's an area in dire need of improvement, and they're showing major promises in enabling gene therapies to treat essentially all diseases. This is small interfering RNA for silencing genes, mRNA for expressing therapeutic proteins, and then you've heard about gene editing. So go in, if you have a defect, Huntington's or cystic fibrosis or whatever it is, the potential is there for very specifically changing the genome in that area so it produces the right protein. Now
Peter,
yes.
for the small interfering RNA, do they have to be replenished, or do they just, once they get in, that there's...
No, this is you have to go in once every, the drug we developed, the most recent drug we developed was every 3 weeks. So it's to silence a particular gene. Now, the technology is rapidly evolving. Some of the oligonucleotides now will give you longer times than that, but the one that's approved clinically is 3 weeks. Okay, so for those of you that are aware of the biology of the situation, nature uses lipid nanoparticles for delivery. One of the reasons why lipid nanoparticles, or LNP, as I often say, have a really substantial need. This is a transport elements. In this case, this is a virus, but it's intercellular transport in various forms, used vesicular systems with lipid bilayer, and as you're aware, cholesterol and everything else, in terms of hydrophobic compounds, gets transported in your body using materials with a monolayer of lipids around the outside and a hydrophobic core. We use both of these systems, or models of both of these systems, in what we do. So for small molecule drugs, this is one of the most obvious problems you can imagine. Right now with a cancer drug, for example, They may have tumors wherever, they inject them with the drug, and less than 0.00, and actually there's a couple more zeros in there, 1% actually gets to where you want it to go. So 1 gram tumor and then 85 kilograms, you can do the math, but it's a very, very small percentage. And so, then you have all the nasty side effects resulting from that. So it's a simple problem, easily stated, and it's one that we are going to beat one way or another in the nanomedicine's effort. And I think people in this room might very well be able to contribute to that. So we just need systems that get more accurately to that site. So this just indicates there's been a lot of work where people try to put targeting ligands on the outside and then say, okay, well, let's target it to that tissue. 30 years of work has gone absolutely nowhere. There's just too many biological barriers to overcome. And I'm sure that the way forward is going to be by having bifunctional systems where you have something in your carrier. In this case, I'm just illustrating as a gold nanoparticle, but we can craft anything we want to here. 5 nanometers, these are, well, I'll show her 5 nanometer GMPs, gold nanoparticle. You want a quantum dot, you want iron oxide, you want whatever. We'll be able to, as long as it's negatively charged, we'll be able to encapsulate it along with a payload. And so what we haven't got right now is a way to get these things to release. So you want them to blow up. And so we want to have external radiation, we inject these things in, they circulate around for a long time. In a certain region, we want them to release this drug. Yes?
So when you say external radiation, do you mean X-ray radiation or do you mean any energy source?
Any energy source. So this could be, this could be laser, it could be electromagnetic fields, or just the magnetic field oscillating that's induced some motion in the, say, an iron oxide nanoparticle. Really, it's quite open as to the type of technology that one might use.
Are there particular wavelengths of electromagnetic radiation?
Yeah, you'd like to be in the infrared or, in terms of penetration. Of course, when you're dealing with RF and with magnetic fields, you don't have that limitation, or with X-ray either for that matter. But the trick is, how can we make these things leaky where we want them to make them leaky?
Could ultrasound work?
It possibly could, but these things are a little small. We're in the 100 nanometer range. We're going to find they're not necessarily susceptible to ultrasonics. So this is just indicating some of the systems we have. You can see the 100 nanometer bar there. So the red here is just indicating 5 nanometer gold. And then the blue is indicating the doxorubicin, in this case, an anti-cancer drug, which we can accumulate into these systems at such high levels that it precipitates out into nanocrystals inside these systems. So these are the type of systems that if we put them into a person, for example, we can make them circulate for the half-life of a day or so. And so you can imagine just something where you had a local radiation of whatever it was, energy source, and just have it paying out in a particular region as it goes circulating around your body. Remarkably, these things are processed by your liver and excreted in a relatively non-toxic fashion. And so you can really see the potential for a non-toxic, but very effective drug for cancer and other disorders. So that's one example of an area where I think that the potential for interaction with this group, I think, is really there. So this would be the kind of idea that we'd be trying to move towards. And for those of you that, and all of us have been affected by cancer in terms of family members or friends, this would be curative, I'm sure, for many, many forms of cancer. We can get this going. So it's a neat problem. In terms of gene therapies, well, this indicates a couple of things here. The siRNA, the small interfering RNA, you get this a big molecule, 13,000 molecular weight. If you get that inside a cell, it will very specifically cause just one protein not to be made. So if you have a protein that's causing some pathological effect, you can in effect shut that down. Now, this hasn't been able to be used as a therapeutic before because these things inject them into the body, they get degraded, they don't end up where you want them to, Even if they did, they can't get into cells because they're so big. And so this is where the delivery system and technology comes in. Similarly for mRNA expressing a therapeutic protein, etc. I'll give you one example of the power of gene therapy. This is a drug we got approved last year for a disorder called hereditary amyloid, something you've all heard about it. The amyloid transthyretin amyloidosis, but it's basically a protein that's made in the liver, and it's secreted into the circulation. And if there's big proteins, so can be a lot of mutations. If there are mutations are of a certain form, it leads to the formation of fibrils, long fibrils in material, which are deposited in wherever, most organs, but they have particularly bad effects in the nerve tissue and in heart, in cardiac tissue. And so it's about 50,000 people worldwide, or the Western world, that suffer from this disorder. Right now there isn't a therapy. And so this is just indicating some of the nasty side effects. It's a wasting disease. So there's GI involvement. Certainly, from the point of view of neuropathies, peripheral neuropathies, etc., cardiac problems. To show you how nasty it is, this is just within 5 years of diagnosis. That's the progression, and these are, you can imagine this for an individual because it is a hereditary disorder. That sees themselves at the age of 30 starting to get the peripheral neuropathy that's associated with this. And they'll know the progression because they've seen parents or grandparents go through it. Anyway, so this is the nanoparticle siRNA approach here. We package up an siRNA to silence that gene that's made in the liver. And then if we're really lucky, we can get it to the liver and get that gene silenced. So it's potentially a very simple solution to a devastating disease that has many manifestations. So lots of symptoms involved. So this is where we started on this about 20 years ago, trying to get things from the IV injection right through to the liver and to hepatocytes in the liver. We developed, so this is where the chemistry comes in. We've had a very intense chemistry effort over the last 10 years, or at least 15 years, to get components of the nanoparticles that engender the best result. I'm not really going to go into the way that this occurs. I'll give you one indication. It's basic physics, actually, but this is some ways that you make these systems, so we can, they're ionizable, which makes them much less toxic. Let's just go back here. So it means that at pH 7.4, they're relatively neutral, which is important because a positively charged entity in the bloodstream can be highly toxic. And so, but at pH 4, we can load them up with, say, a really good nucleotide. We use microfluidic mixing as a way of doing this. And so when you're mixing the oligonucleotide with, say, the cationic lipid here, one of the first things to fall out of solution is a hydrophobic or inverted micelle, you might think. Those, of course, aggregate if it's done slowly. To do it really fast, we can have a PEG lipid that will surround that polyethylene glycol. We can trap them in a minimum size, a lipid size that is quite uniform. Anyway, so this is a way of making these systems. This is, say, a microfluidic mixing. We work with Carl Hansen in the physics department to develop this approach, and actually we have a company that's making these type of systems on a small scale and a large scale manufacturing basis. Okay, this is, I don't know if you can see it, but we can have gold, 5 nanometer gold as a surrogate for the oligo, and you can see the curved bun sort of structure here. Where we're entrapping these negatively charged. This is the way we can entrap any negatively charged entity in these systems. I'm not going to go through this in any detail. We're using an animal model to optimize these systems, and this is work that we did with a company in Boston called Alnylam over the course of 2005 to 2012 to develop really optimized systems. And the physics of this is that we're developing systems that on their own will form bilayers. We put them together and they form non-bilayer structures, basically rip membranes apart. And so we have to engender that to occur in the environment of the endosome following uptake. So the design here, design principles are quite, they certainly led us along the right path. Let's put it that way. Over the course of about 7 or 8 years, with 8 chemists working full time in Boston and here, we improved the potency of these systems by about 3 orders of magnitude. This then resulted in a clinical trial for people suffering from this HATTR amyloidosis. So with 150 people in the treatment arm, and then 70 or 80 people in the placebo arm. Placebo is just the saline, so there's no drug in there at all. And then the neural impairment was the primary readout with a number of secondary readouts that came from this. The staggering result here was that these are people, this is looking at the neural impairment score for individuals who are on the placebo, and they're getting steadily worse. For people they're using this gene therapy, if anything, they're improving. So you're taking a established hereditary disorder and reversing it, which is really quite an amazing thing to be able to do. So this is, there was no doubt about the significance or the statistical significance of these results. With a p-value of 10 to the minus 24, you know you've got something that actually is working. I don't know for Avogadro's number, more or less, but anyway, this is the secondary quality of life reports from the individual's muscle strength, be able to walk, put on weight, so all the things were dramatically improved. So you've essentially taken a death sentence and now made it into something people are going to be able to live with. So this really points out the power of gene therapy. It's remarkable. You can really, using the molecular biology that's going on inside the cell, and which we have a lot of understanding of, but in the past, no delivery systems to allow that to be used therapeutically. We can really, this is just one example, this is a primary example. It's the first RNAi drug that's ever been approved by the FDA, of what's to come. And so it's as I say, it's a very exciting time. So not only being able to halt the progression, but also actually reverse the accumulation is pretty neat in terms of, so this is also now enabling, the same approach is enabling other forms of gene therapy, and I'll just go through that in the last couple of slides. mRNA for protein production in vivo, and vaccines and therapeutic proteins are focusing here. I'm not going to talk about the gene editing side, but that's coming into play very, very quickly. So it shows what you can do for those that want to go into the Tour de France. You need a dose of this. This is taking messenger RNA for erythropoietin. A single injection into a pig model, and you get supra biological levels of EPO but you do this for any protein you want to make. So an example of how that can be used, this is where you take an mRNA that codes for an antibody against HIV. So you give that as a predose and then challenge with a lethal dose of HIV. As you can see, this is these mice on the right-hand side were challenged in that way, and they're completely resistant to infection. These ones had a luciferase, another marker gene, and of course are not protected. So similarly, Zika virus, the range here is enormous. For example, the universal flu vaccine is now completely possible because we can get very good immune responses to the stem portion of the hemagglutinin that's conserved right through many strains of flu. So you can see you just have one flu injection for your life as compared to having every year and not being sure what's going to work either. So these are exciting possibilities. So that's basically it. So many applications here for any disease you care to name. What do we need? We need to be able to do these things in a more site-specific way. And we need to be able to visualize it. We need to understand the process of, we understand what happens once they get out of they're taken up by a process called endocytosis. We have to break them out of the endosome, which is a little bag inside the cell. And we like to be able to visualize that much better. Right now, we're not very good at it. There are alternative ways of getting access. We need to enhance the potency of these systems, particularly for different tissues, different routes of administration, and maybe other things that come to mind as a result of seeing some of these possibilities. So with that, I'll stop. Let's open to some discussion.
Great, thank you very much. It's really fascinating. Just maybe we can start by just elaborating a bit on some of these requirements. So, site-specific gene therapy. What sort of different sites are you looking at? What sort of dimensions?
That can be really varied. I mean, one of the things, obviously, the brain is a target of some interest. So we've been working with people in the brain center here, and you can inject into the cortex of the brain, and you can see a gene therapy, or certainly you can get expression or silencing genes in a local region of the brain. Or you can also you can go intrathecally, which is say an osmotic pump that goes into the CNS. Is another. There you're going to be a more global thing. One of the things that would be nice would be able to apply some sort of radiation or some sort of energy source very focused. That would mean that you're only going to get gene therapy in a particular tissue that you want to get it. And that would, right now we're good in the liver simply because we're taking advantage of the natural biological effect that targets things, so the liver. But for other tissues, we're not. And the ability to really localize where something is, where the gene therapy is happening, but it's not happening anywhere else. That would be pretty neat to be able to do that.
You talked about the 20 to 100 nanometer size range, but I'm thinking a red blood cell is a bit bigger than that. So why that range?
This is again, this is biology, but the endocytosis, it's getting things taken up inside the cell. It's their maximum size they take up is around about 100 nanometers. You can get bigger things taken up, but it's more specialized cells that do that, like macrophages and basically the cells that are gathering up things in the blood that are formed.
So you could have a bigger transport medium that then, if you broke that apart, into smaller.
Yeah, that's certainly another possibility.
And then on the imaging side, or visualization, so you're hoping to see things that are really at the 20 to 100 nanometer sort of size.
Yeah, I mean, obviously you're giving billions of these particles at any one time, so it's not just one. There would be certainly enhancing the resolution of these things would be something that is, would be very, very good to do.
And is it interesting to have better models of these that are like tissue models, that sort of thing? Yeah, I mean, and this would be, if we could just take us, one of the things we've been doing here is we're optimizing on the basis of in vivo behavior. We don't yet have, and actually we probably never will have, a model of what, something that's going to work in vivo, where we have an in vitro, just a tissue culture medium. But it would be very nice to be able to check out exactly what's happening once it gets inside the cell. The reason why the translation is difficult is because things get pulled out of the circulation before they get to where you want them to go, and so you need to have that side of things going on, and that's what happens most of the time, actually. So something that works in an in vitro situation is, not at all guaranteed to work in vivo. But once you get it to a cell, what we would like is to be able to follow very accurately what happens. Some of these systems work very well. We think it's because of enhanced cell delivery, but we don't have any proof of that yet. And then when you're saying alternate ways of
Can I?
Yeah.
One little follow-up.
Yeah.
What's your feeling about the ways to improve the visualization. Is it to add additional materials to your nanoparticles to improve contrast with current imaging, or is it to modify the imaging systems so you don't have to modify your nanoparticles?
Well, modifying a nanoparticle is simple. As I said, I mean, if you want to put any fluorophore or quantum dot and anything in these systems, that's straightforward for us to do.
Okay.
So we sort of need the people that understand those systems and to tell us what to do or what kind of things they would like to have put in there. That's where the collaborative part of this comes in.
And then other ways of gaining access. So at the moment, it's by endocytosis. So basically, these, if I understand correctly, they fuse with the membrane of the cell and then the contents.
Yeah, we kind of hijack a naturally occurring system. These are when you eat fats. It goes into your gut, and then the fats are partially degraded, and they migrate across the lumen of the gut, and then they're reassembled in something called chylomicrons, and then they go to the liver where they're packaged. They're taken up into hepatocytes. They're packaged in the form of low density lipoprotein, HDL, and all those things. And it turns out that these systems with a hydrophobic core are treated in a similar way. And they adsorb a lipoprotein called A12E, and they just go straight up by the mechanism that's used by the chylomicrons. So it points out really the ways you have to use biology as well here to get the best effect.
But I guess there have been other ways that people envisioned getting.
It's getting into cells, but even more getting out of the endosome. That's been the big issue. We're still very inefficient at that. I mean, 3 to 4% of what's taken up, only 3 to 4% gets out. And so if we can blow these things up a little more, and again, it's back to that thing where how can we agitate this or find some way of making them more efficient in that regard. This might be where this focused gene therapy comes in.
And then potency just means you want a larger dose or
a more potent system. I mean, if we could envision a system that would, instead of 3 or 4% gets out, 100% gets out, that would make it a heck of a lot more potent. So in other words, if you had something that was going to break out of the endosome with more efficiency, then that would be really obviously a good thing.
And then other routes of administration would be other than injection into the bloodstream.
Yeah, right. So here we're taking advantage of this natural tropism that I mentioned to hepatocytes. We have ways of altering that. So we're looking to say, okay, can we get these things? And we know we can. It's just not as efficient. Into immune cells, for example, so we can modulate the immune response, or into bone marrow, stem cells in the bone marrow, leukemia, and all sorts of other things are possible to go after in that context. And so these and then the other area that we're certainly exploring is direct injection, intraocularly, for example, for eye disorders. I mentioned the brain is, we were very good. So from a neuron point of view, we can certainly introduce these large molecules into neurons. The thing is you have to make it into something that could be a therapeutic. There are therapies now that do rely on an osmotic pump going into the CNS. So for serious disorders, you can see that might be our route. Going after Alzheimer's is certainly a possibility now. See the ways of going at it. But anyway, so these are the kinds of things. Yes?
Is the proposal restricted to external radiation, or are you also considering chemical triggers, for example?
If we can make it, one of the things we were first looking at was